Today we're reviewing for test number 3. One of the topics on test number 3 is rational functions, so this is the last section back in chapter 4. When you're graphing rational functions, we're using a lot of asymptotes and intercepts. I want you to sketch the asymptotes first using a dotted line, and then make a careful sketch of the actual graph of the function using a couple of nice points. You don't have to have a lot of points, but a couple just to help you locate where the function is. So the first one we're going to look at is x over x plus 4. The vertical asymptote we can find by setting the denominator equal to 0, giving us x equals negative 4, which is this dotted line here. The horizontal asymptote we can find by comparing the degree of the numerator to the denominator. Since they're both degree 1, we take the ratio of the leading coefficients. Those are the red ones I've written in here. So y equal 1 is the horizontal asymptote of the function, which is the red dotted line here. The domain of this function will be all real numbers except for negative 4, so that's where the function's undefined. And then I use my calculator in a little bit here to help me find a couple of nice points and sketch in the function, which is in two different pieces. And then showing that it approaches the asymptotes with the arrows, but does not cross the asymptotes. Second function down here is 3 over x squared subtract 9, which I can factor to 3 over x plus 3x subtract 3. So the vertical asymptotes are going to be x equals positive 3 and negative 3. And then the horizontal asymptote, comparing the degree of the numerator to the denominator. The numerator's degree 0, the denominator's degree 2. Since the numerator is smaller degree than the denominator, the horizontal asymptote is going to be the line y equals 0, or just the x-axis. So I've sketched in the asymptotes here with dotted lines, and then found a few points, and then using those, the green line here is the actual function. Okay. Graphing exponential log functions, again, these have asymptotes also, and want to think about the domain and range of these functions. Again, show the asymptotes with a dotted line, then sketch the function. So a couple ways to think about this one. I like to think about it as being the graph of 2 to the x shifted up 1. So I know the graph of 2 to the x has a nice point at 0, 1, and a nice point at 1, 2. Those both get shifted up. 2 to the x has an asymptote along the x-axis, and so shifting that up gives me an asymptote at the line y equal 1. So I have a horizontal asymptote y equal 1. My domain's negative infinity to infinity, and my range is 1 to infinity, not including the 1. For the log function, this one's log base 2x subtract 1, so I know it's my basic log base 2 function shifted to the right one. So the nice points on the log base 2 are the points 1, 0 and the points 2, 1. Those both get shifted over for these 2 points here. Normally the log function has an asymptote along the y-axis, along the line x equals 0, but that's been shifted to the right one, so I have a vertical asymptote at x equal positive 1. So that makes my domain 1 to infinity, my range negative infinity to infinity, and then sketching the actual graph here with the black line. So again, don't trust your calculators on these. It'll make it look as if the function stops at a certain point, when it actually continues down to negative infinity. Okay, so another thing you need to know for the test are the properties of logarithms. If you need to, first thing when you start your test, write them all down just so you've got them there for reference. So if we're adding 2 logs, it's a log of the product. Subtracting 2 logs, it's a log of the ratio. If we have a log to a power, we can pull that power out in the front to make it a multiplication problem. And then we've got some basic properties. A log base a of 1 is always 0. The log of a number to the same base is always equal to 1. And the log base a of a to a power will always equal the power. Those come in handy. And then you also want to know the change of base formula. So you can change the base to any log that you want as long as you're consistent. I usually just use a natural log. Common log works easily also. Okay, some examples of some exponential and logarithmic equations. You want to be able to solve them algebraically and show your work. Remember, you can always then, after you've got the exact solution, find the decimal approximation, plug it back in, make sure it actually works. So here's an exponential equation, 3 to the x subtract 1 equals 10. So I started off by taking the natural log of both sides. That allows me to pull the exponent out in front using my properties of logs. And in this case, I distributed the natural log of 3. I also could have divided. There's a couple ways usually to do these. And then I subtracted the natural log of 3 to the other side. leaving me with just the 1x term here on the left, and then I can divide by the natural log of 3, so this would be my exact solution. Then I've got a log equation here, log base 3 of x plus 2 equals 3. This one, once I rewrite it in exponential form, swinging the base of the log around to be the base of the exponent, 3 to the power of 3, I've got a much simpler looking problem. X plus 2 equals 27, so x equals 25. This log equation is going to take a little more work, and I guess I've got that in the way there. Here we go. Log base 2 of x subtract 2 is 2 subtract log base 2 of x plus 1. First thing I'm going to do is bring this log over to the left-hand side. It's now addition. So I've got all my logs on the same side, and if I'm adding two logs, I can combine them in a single log using multiplication. And then once I'm in the single log equal to a constant, I can switch to exponential form, give me 2 to the power of 2, and then foiling these two binomials out, I've got a quadratic equation. This one factors nicely, and I get two solutions. But you want to watch out, especially with the log equation, sometimes you pick up extraneous solutions. X cannot equal negative 2, because if we were to go back to the original function here and use negative 2, I'd have the log of negative 4, which is not defined. It's not a real number. So our only solution to this particular equation is just the x equals 3. It looks like I've got a little bit of time. Let me go find a couple more examples to show you. Okay, here's one out of the book. It's very similar to the one we just looked at here. So we've got a log plus a log equal to a constant. We can combine them together with multiplication, switch to the exponential form, and then we've got a quadratic. This one didn't factor, so we can always use the quadratic equation, and we get two solutions again, but only the positive one, the 2 plus the 2 square root of 2, will actually work in the original function. Yeah, I just remembered we need to look at a story problem. So let me jump back again here. There we go. I pulled this one off of an old test. So we've got a population of jackrabbits. It's 180 in the year 2000, but by 5 years later, in the year 2005, the population's grown to over 3,000. So since 180 is my base starting number of jackrabbits in year 0, I'll call 2000 year 0. That would be my value here, my starting value, and I don't know the growth rate yet. But I do know after 5 years, my population's grown to 3,330. So I can solve this equation for r. I'll divide by the 180, and I'll take the natural log of both sides. That lets me get at the 5r, and I can divide both sides by 5 to get my rate. And so my model is 180 e to the 0.584t. And then I can take this model, substitute in values of t to calculate the population of jackrabbits in a particular year. Or if I want to know in what year the jackrabbits grew to a certain number, then I can put that in for a and then solve for t.